This conference will now be recorded.
My screen, am I right?
Yeah, I will get you that first. Let me see. Michael, can we put Francisco as a presenter? Let's see. I think I have the, I can do that. Yeah, make presenter. Here we go. You got it?
Yeah, I got it.
Awesome. So we'll present you here and then we'll get going. So, okay, so welcome everybody. So we have today a talk from Francisco about White Rabbit and high accuracy PTP and the background and applications. So Francisco is the America's Tech responsible at Seven Solution. He holds a Ph.D. in Telecommunications Engineering from University of Granada. Francisco joined the Timing Keeper group at the University of Granada as a researcher in 2015, where he specialized in ultra accurate time transfer systems and the focus on the development of White Rabbit technology. Afterwards, he joined Seven Solutions, where he worked as an FPGA designer until he moved to the US to lead the Seven Solution expansion in America. He combined his work at Seven Solutions with his studies for a PhD in telecommunication engineering. This combination has provided Francisco with a strong technical background on high accuracy time synchronization and deep knowledge on timing application in the industry sector. So with no further ado, Francisco, the floor is yours.
Okay, thank you so much. So today I will make a presentation where I will present White Rabbit and the high accuracy PTP profile, which is more or less the same. But as a couple of, I'm not sure if it was a month ago or so, you had another presentation explaining the technical part of White Rabbit. I won't focus that much on that, but on the different applications that we find when we are working with this kind of time synchronization technology.
And maybe it's worth to mention also that that previous talk, which was by Masic from Masic Lipinski, I think, from hopefully I pronounce his name right, from Stern, which is also recorded. You can just find it on or Wiki. Yeah, Francisco.
Yep. So in any case, I will go. I will do a little introduction just in case anyone missed that talk or needs some kind of refresh on the topic. White Rabbit is basically an implementation of the PTP standard, the IEEE 1588, but with a focus on high accuracy. Its goal was to achieve sub-nanosecond accuracy in the time synchronization. As it is an implementation of PTP, it is basically the same in a theoretical aspect. In this sense, it can be integrated in Ethernet network, in this case using optical fiber for the distribution. It is interoperable with any other time synchronization protocol, the same that we could do with PTP. For example, we can transform from White Rabbit to PTP or to NTP, or we can provide analog signals like pulse per second signals. It is a distribution technology, so it basically, it doesn't generate the time reference. It gets a time reference and distribute that reference through the network. Therefore, it is resilient to GNSS disruptions if you are using as the reference as on atomic clock, or you are using any different PNT source, which is not GNSS. It has some advantages in comparison to PTP, which are a pre-calibration model for certain scenarios that avoid many of the inaccuracies that you can find in PTP deployments, and at the same time, it is escalable to thousands of nodes and metro areas. Long story short, a comparison between a standard PTP precision, you see the blue line here, and the White Rabbit precision in orange, is that White Rabbit is much more precise and much more accurate than PTP or previous or standard PTP links. Another example, this one from production. This is an example in the German stock exchange, where they synchronized multiple of their time stamping machines. You can see the difference that they had when they were using PTP and when they upgraded the network to White Rabbit. In this case, a 100 times improvement in the time synchronization for all the different time stampers that they have. A short review on the background of White Rabbit. White Rabbit relies on layer 1 synchronization. When we are working in Ethernet networks, all the devices share the same nominal frequency, but the actual frequencies in the different devices are different and are slightly different between one compared to the other. And this means that over the time we have a clock drift. What we do with White Rabbit is layer 1 synchronization. What does that mean? We basically retrieve the clock from the Ethernet link, and what we do is to distribute that frequency or to synchronize all the different devices to share the exact same frequency, avoiding this clock drift over the time. Once that we have performed this frequency distribution, all our devices are sharing the exact same frequency. What we do is starting a PTP exchange. With the PTP exchange, what we do is exchanging PTP packets between the master and the slaves, or the leader and the followers, and we timestamp those packets. With the information from those timestamps, we are able to measure the time of one important thing that we do when we are working with White Rabbit is that we take advantage of the fact that we have synchronized devices, we have the same frequency in all the different devices, to perform clock phase measurements that allow us to timestamp every PTP packet that we exchange with picosecond level precision. This means that when we are calculating the time offset, the calculation is much more precise than other implementations of PTP. So basically what we do with that information about the time offset is move the internal clocks till both of them are exact copies. An important part that I mentioned before was the calibration. As you see here in the right side, all the red lines or the red packets that we exchange are in most cases related to calibration. Calibration is important in PTP because if you are familiar with this, with network protocols for synchronization, you know that one of the main source of errors when we are calculating the time offset between devices are the asymmetries in the link, because we perform, or we suppose that the latency from the master side or the leader side to the follower side or the slave side is the same that backwards. What we do here when we exchange that calibration information is actually avoid guessing or supposing that this fact is actually happening, but providing information about the internal delays in the devices, the asymmetry, the expected asymmetry in the link, and all that information. So basically here, what we do is to exchange the information about the internal hardware delays, also the delays because of the SFP transceiver that we are using, and also the asymmetry in the link. And with all that information, we are able to correct any kind of inaccuracies because of the asymmetry in the PTP exchange. However, this is something that we can do and that we provide pre-calibrated devices, and they work in local areas using bidirectional SFPs. And depending on the SFP, the typical transmission power or the reach is in the range of a few kilometers. So for local areas, it's quite good, but it doesn't work everywhere. When we are working with other kind of networks, like for example, DWDM networks, in those cases, what we do is performing field calibrations. So we still maintain all the information regarding the calibration because of the hardware and because of the SFPs, And in that case, what we can do is calibrate the specific asymmetry for the actual link that we are using to synchronize using white rabbit devices. Examples of topologies, a couple of them. In the right side is a simplified one where we have a single time reference providing time to the first white rabbit device, what we call the grandmaster white rabbit device. And this white rabbit device is responsible of distributing that time reference to the subsequent white rabbit devices using optical fibers. All the synchronization from the time reference to the different white rabbit devices that we have in each location maintains the sub-nanosecond accuracy. That's the main feature of white rabbit devices. Later, we could have multiple interoperability options in order to provide this white rabbit information, timing information, to other consumers that are not able to speak white rabbit. For example, we could use PTP, we could use PPS, distribution pulse per second, or we could even integrate white rabbit capabilities in the final nodes. On the left side, we have another topology, but adding redundancy. White rabbit devices are pretty similar to PTP devices, and therefore you can have all the typical resiliency tools that you have for PTP devices. In this case, we are using two different time reference. One is a GNSS receiver, and we have a backup atomic clock using a redundant grandmaster layer of white rabbit devices, and those devices are providing redundant links to the subsequent layer of white rabbit devices. Those white rabbit devices could have multiple time sources at the same time. They could include rollover capabilities in case all the time sources are lost, etc. Finally, we will have a layer, which is the one that is used for this interoperability with any other third-party devices that don't support white rabbit capabilities, like for example providing PTP or providing the legacy pulse per second signals, etc. Again, important, white rabbit is a distribution technology, so we need a time reference, an atomic clock, a GPS receiver, any other kind of alternative PNT source. That time reference provides its internal information using pretty standard time synchronization signals like 1 pulse per second and 10 megahertz clock, plus an NTP feed for time of the information. And once that we have those signals that, as I said before, they are pretty typical in any kind of timing device, we are able to synchronize the first device in the network, which is the white rabbit grandmaster. The white rabbit grandmaster is the device that will start distributing white rabbit. So it's like the top device in the white rabbit topology, and it will distribute that white rabbit information using optical fiber to all the boundary clocks, or also the ordinary clocks. So basically, depending if the other white rabbit devices redistribute the information or if they are the final, the last level in the network. Again, discussing about failover and rollover, important, for example, in the boundary clock layer or also in the grandmaster layer. What we have done with the white rabbit devices is to integrate a failover algorithm. This algorithm basically have multiple time sources that can be white rabbit sources, can be PTP sources, can be external time sources from an atomic clock or a GNSS. And we have an algorithm that chooses which one of them is the active clock in the devices using priorities. Once that we have chosen the time source, the active time source, we have a virtual clock that we call, which is the one that we use to redistribute timing to any other subsequent layers. White rabbit was first created for particle accelerators, and one of the main requirements in particle accelerators is distributing frequency. So jumping between different time sources might be quite problematic in those scenarios because we have a lot of systems that rely on the frequency itself. So an unexpected jump will actually affect the precision or the performance of the system. Therefore, what we do is instead of using a typical best master clock algorithm, which is something that we could integrate in White Rabbit, what we do is using priorities and fixed status. So the algorithm basically only jumps from one time source to the other in case of failure. So instead of computing different the clock accuracy for different or the clock quality for different sources, what we do is we have a primary source. If that primary source fails, then we move to the next one. In this case, imagine that we have the first White Rabbit 0 source. It fails, we jump to the next one. In the next moment, the first time source becomes available again, but what we want is to avoid jumping again to the other time source, because our goal is in all cases minimizing the number of jumps between time sources that we have. So what we do is that in the next moment, if the current active time source fails, we can jump to the previous one, reevaluating the whole priority, or we can move to the next one. Of course, if you are the operator of the system, you can force the devices to jump to the previous one. But what we don't want is that to be performed automatically. We want to have full control of what's happening in the network and what is the origin of time in our network. Finally, if we lose all the available time sources, then we can jump to rollover. And with rollover, basically we integrate a pretty stable oscillator that guarantees this 1 microsecond after 24 hours accuracy, even when we are not following any available external time source. Finally, in the interoperability layer, as I mentioned before, White Rabbit, PTP high accuracy, several profiles of the PTP standard, NTP, analog signals, or other kinds of time synchronization mechanisms are supported by White Rabbit devices. So now I'll move to the application part. Okay. So again, this is the same graph that I showed before. The time reference, the different devices, the grandmaster, and then the different devices that we have in the network. So imagine that what we want is to support or to scale the White Rabbit network, providing in the final hop PTP, or if we want to have a full White Rabbit network. In this case, there are different devices. For example, the White Rabbit switch from the open White Rabbit community. We have also the White Rabbit Sec system, which is one of the 7 solutions products. In this case, it's a device with multiple optical interfaces that provide White Rabbit and PTP. And they include all the failover mechanisms. They include the internal management tools. So at the end of the day, these boxes are pretty much regular network devices in terms of management and monitoring, but providing high accuracy time synchronization. And that's the goal. We could have a different scenario. For example, if we don't want to have a fully White Rabbit compliant network, but we want to just have like a core layer of high accuracy and then move to regular PTP, or if we want to provide push per second signals directly to the consumers, which is a pretty typical scenario when we are working with different network equipment. So in those cases, we have the White Rabbit 10 time providers. So the time providers also support White Rabbit and PTP, but the number of optical interfaces is much lower. But the difference is that they have all this expansion, or there are different models that can provide multiple analog outputs in just one single box. This is intended for scaling the number of users that can use that reference using just one single box. Again, these are regular network devices, so all in terms of monitoring management, these are pretty similar to what you will have out there.
One thing, Francisco, there are a bunch of questions coming along. Do you want them to be answered in a question period, or you don't mind if you answer them on the fly?
Yeah, I can answer them. Just let
So
me
one
look
of them I think was about how do you, like, basically make all of us know, like NTP and PTP are pretty vulnerable to the asymmetry, and you mentioned that White Rabbit has a mechanism to mitigate for it. Would you elaborate on that, or you want to put it in the end? Like, it's good if we can on the fly answer them actually.
Yeah, sure. The thing is that I'm not very sure about where is the chat here. I see that they are popping up, but
on the
yeah, I found it.
Yeah,
I found it. Thank you. So yeah, the thing about White Rabbit calibration, especially in local areas, what we do is that, of course, we take care of all the internal delays, hardware delays, SFP delays, because we know the models that we are using. And in terms of covering the asymmetry in the link, when we are working in local areas, what we typically do is also knowing which kind of SFP we are using. If we are using bidirectional SFPs and we are using different wavelengths for transmission in one direction and transmission on the other direction, we can actually foresee the asymmetry that we will generate in that link. So it's something that we can compensate if we know the optics that we are using. In other cases, if you are using bi-fiber SFPs or different models, there are ways also to calibrate for those specific SFPs. So basically, it's a one-time calibration that we do, and then you can use that SFP as many times as you want, because the devices will automatically compensate independently of the distance of the link in a local area. This can also scale to long distances. For example, the higher distance pre-calibrated link that we have deployed was near 350 kilometers. We had 5 White Rabbit hops, and we use it for that pre-calibrated optics, because we knew we had a dark fiber and we knew the optics that we were using, so we were able to just get the values in the devices, and it was a plug and play deployment.
So the bottom line is every device along those hops has to be White Rabbit enabled, right? Otherwise, this is not going to work.
If you want to deploy a White Rabbit connection, you need to have White Rabbit devices, White Rabbit compliant devices. So, for example, you cannot use a White Rabbit device, then a PTP device, and then again a White Rabbit device, because the PTP device doesn't support White Rabbit. However,
understood.
There are
and does this also work for copper ports?
Yeah, White Rabbit can be deployed on copper interfaces. However, the copper interfaces are much noisier than optical interfaces, and therefore typically the distances that we can reach with those kind of links are much shorter. The recommendation is working with optical interface.
Okay, yeah, Francisco, one question.
Mm-hmm.
This is intended to mix a current solution of PTP deployment, or just to button and build a new network with this kind of equipments? I mean, I have deployed in Claro Argentina phase TDD support network. So I wanted to know if you are competing with clock devices like microchip, for example, or ADVA, I don't know, or is a complement with them?
I mean, we can do both. It depends on the actual application. So keep in mind that when we are working with White Rabbit devices, what we are aiming for are high accuracy applications. So not all high accuracy timing applications require to have this sub-nanosecond level accuracy that we are speaking about when we are working with white rabbit. Therefore, it depends on the customer's need. We can replace all the previous PTP network or NTP network, depending on the application, or we can complement the current network. So you have, for example, if you check here the topology, that will be the case of the cabinet 2. In cabinet 2, we have one part of the network, which is white rabbit, to maintain this sub-nanosecond accuracy. This is, for example, if you want to save some time budget in a long distance link, or if you have at the same time the scenario of cabinet 3 and the scenario of cabinet 2. Cabinet 3 will be like the high accuracy part of your network using PPS for a very specific part of it. And then we will have a second part, which is white rabbit as a core network, providing timing to PTP and distributing it using PTP.
Raghuram, do you want to ask a question as well? So Raghuram was asking.
I think I asked my question about the asymmetric part, but I do have one more question, Francisco. The devices that you showed, actually the devices in the top of the cabinet block that you show in the slide, are they intended to be primarily switches that offer the white rabbit functionality on every port because of your customized FPGA in there, or are they purely just timing recovery devices?
So the first, the top layer device, this one here, the white rabbit 16, over here, this is, I mean, the design is exactly the same, but they can work with different roles. We have one role which is the grandmaster that logs using analog inputs, the 10 megahertz clock and the 1 PPS clocks. And these are the signals that we use to get a reference in the network. And then the same devices are able to distribute using optical fibers and using the white rabbit protocol to distribute that time source with the sub-nanosecond accuracy. So virtually, it's like in most cases when we are working in data centers, is we have one white rabbit device near to a GPS receiver, and what we do with the white rabbit network is generating copies of the GPS receiver signals in all the different cabinets where they are used by the customer. So it's like having a zero budget error, less than 1 nanosecond from the reference that you have in the GPS receiver that is feeding your network.
So one more thing, like about the asymmetry that you mentioned, like also knowing the optic, like basically the optics on the both sides and so on. You require certainly to have the switches be first synchronized in order to do basically the one-way measurement, right?
Mm-hmm.
While then you have that synchronization also provided by the white rabbit. So there is a chicken and egg here. Like how does that work?
Yeah. So when we are working, when we are working in local areas, pretty simple. We have a point-to-point connection between white rabbit devices. So it's clean, it's easy. We have control both ends of the network. That's okay. When we are going to long distance scenarios, what we typically see is that we start working with DWDM equipment, and in those scenarios we can find passive equipment, multiplexers, filters, DCMs. We can find active equipment, amplifiers, and we can find electrical equipment. I will catalog them this way. So there are devices that, for example, transponders that actually transform or retime the signal that you have in the link. What we have found over different tests, and it's something that I will show also later, we are typically fine working with synchronous Ethernet compliant equipment for DWDM optics, and we are also, of course, fine working with any kind of optical equipment that doesn't retime the signal. So as soon as we are able to perform the frequency distribution with an accuracy that is, or with a precision which is good enough, that's okay for White Rabbit to work.
And then Alexis had a bunch of questions. Do you mind? You can ask them directly.
I was just wondering, you answered my first one in the things, but when you're talking about BiDi, does the chromatic dispersion inside the fiber optic cables contribute to asymmetry in the links when you're using BiDi?
Yeah, of course, and the different propagation speeds also in the link are actually the main source of asymmetry in those cases. However, when we are working with bidirectional SFPs, we typically know the wavelengths, or at least the nominal frequencies that those SFPs are using, and therefore we can estimate the difference. However, and this is true, some of those SFPs are not very precise on the actual wavelength that they are using, and in some cases you can find small differences, especially in long distances, depending on the SFP. In those cases, we can work with other optics, like for example the WDM optics, that are in many cases much more precise than bidirectional optics, or we can check the different vendors and see how well they are performing.
Wonderful. Let's continue then.
Okay, perfect. So last scenario when we are speaking about synchronization, which is basically providing White Rabbit till the end node. You know that, and this is a conversation that you had also with Magic Talk. White Rabbit can be integrated in devices. The only main requirement is having an FPGA, and there is even an open core that allows that to do that in some applications. In the 7 solution side, what we have done is also allowing or developing an IP core, which is the high accuracy timing IP core, that can be integrated in different families of FPGAs. So it's basically the same that you had in the open, but we have worked over it. We have developed it to improve the integrability in different projects. At the end is basically the same that White Rabbit. You have a fiber connection from a White Rabbit compliant device, and using layer 1 synchronization and using PTP exchanges, you are able to synchronize the final. The main, and again, as this is intended for local connections, you can avoid the calibration. The main goal for this IP core is to be integrated in network equipment that support FPGA. So, for example, L1 switches or NIC cards are the main goal for this IP core, the high accuracy timing IP core. For example, we have an ongoing integration with the Arista 7130 switches, which are the models specialized for finance applications. We have also, and this is something that the Cisco team mentioned not so far away ago for using the distribution list, the email distribution list of this project. We are also integrating this IP core in the Cisco Nexus 3550 series, and these are also some devices that are typically specialized for trading applications, where sub-nanosecond accuracy is basically one of the main ways to synchronize the network depending on the different players. So in those places where we have this high performance computing is where we are right now working more to integrate White Rabbit capability, because sub-nanosecond accuracy is actually relevant, for example, measuring latencies, time stamping packets, etc. So now moving into the use cases and case studies for the technology. White Rabbit, from its very beginning in the science sector to finance, as I mentioned before, with the integration in these switches, or to other different applications like telecommunication, defense, etc. It's used in many different sectors. So first case, and I show some results about it. It's the visibility network for the German Stock Exchange. Basically, we provide time synchronization using White Rabbit to the timestampers that are located in all links in their data center. This way, they can capture the packets in each one of the links and develop this visibility network to calculate, for example, the latencies and to have a better understanding of what's happening in the network, etc. Second use case, this one also in the finance sector, but in a different area. In this case, we had the Spanish Stock Exchange. They have two different data centers around. They are located in the city of Madrid, but they are 44 kilometers apart, 27 miles. So what they wanted is to distribute the time reference from one of the locations to the second location. And we did that using a public telecommunication network. We were able to distribute this with sub-nanosecond accuracy. And in the second location, what we did in order to have traceability to UTC was to deploy a White Rabbit GPS discipline oscillator, the DOWR. This device was calibrated against a National Metrology Institute, so we had actual traceability of the accuracy. And thanks to this device, we were able to provide this plus minus 15 nanoseconds traceability to UTC, even when the relative synchronization between the two data centers maintained the sub-nanosecond accuracy. Later, we had the holdover in case that we lost the time and link at some point. And the holdover showed these results, this microsecond after 24-hour result in this second location. So even when we are learning from a time reference, which is 44 kilometers apart, we were able to maintain this microsecond accuracy after 24 hours. This case is extrapolable to any other proprietary trading firm in the finance sector. They typically work in financial hubs, for example, New Jersey, Chicago, London, where there are different data centers in a metro area. And what we do with White Rabbit is to provide a single clock domain between all the different data centers that they have. Before, they were relying on GPS receivers in each one of the locations. And basically, that meant that the correlation of data between the different data centers had an error because of the accuracy of those GPS receivers. And this is something that we have removed with White Rabbit. At the same time, we are providing resiliency, because one of the main source of error when we are working in production regarding timing is the GPS receiver failing. Because of interferences, because of jamming, it's the main cause. So what we are doing here is distributing time using fiber. So we have a single clock domain, and only in case that the fiber fails, we can redirect the time synchronization, or we can jump to the GPS receiver, depending on the scenario. At the same time, we integrate this interoperability, PPS for a part of the trading network, PTP for a different part of the PTP of the trading network, depending on the needs of the customer. These scenarios are for finance, but when we are speaking finance, we are basically speaking about data centers. Finance happens in data centers. So everything that we cover here, synchronizing multiple data centers, synchronizing inside one data center, providing resiliency to GPS, having interoperability or a core White Rabbit network that then can provide time synchronization to different parts of the network, it's something that we can maintain. For example, also traceability to UTC. Those kind of things we can do with White Rabbit devices when we are working in a data center environment. Inside one data center, again, sub-nanosecond accuracy, plug and play links, because we know the optics that we are using, no kind of calibration, so it's just having fibers connecting the different White Rabbit devices, and different interoperabilities depending on what we are synchronizing. When we go to the inter-data center, so we are connecting multiple of them. In those cases, we have typically DWDM distribution. If we have the DWDM distribution, we can calibrate for the asymmetry in the link, ensuring the sub-nanosecond accuracy. So it's a one-time calibration to ensure that everything is working fine. And this can be used for resiliency on the GPS receivers. It can be used to calibrate the GPS receivers. It can be used for have a single clock domain between the different data centers, improving, I'm not sure, there are different applications, for example, distributed databases or latency measurements in different parts of the network, etc. We have another use case, which is telecom. In telecom networks, we typically have a central location where we have the EPRTC clocks with the cesium backups and with the GPS, and then we have a lot of fiber connecting the different sites. What we can do in those cases is having a redundant time source in the main location and distributing it redundantly to the other locations that we have in the network. At the same time, one of the suggestions that we are proposing lately is basically, if you have this kind of scenarios, what you can do also is to close loopbacks to the main locations for monitoring of the time performance in the different parts of the network. So this is another possibility, and that's something that you can do in the White Rabbit devices now that these multiple time sources are supported in one single device. So you could be using one White Rabbit device for distribution of time, and you could be using a different White Rabbit device for measuring time, or you could combine both of them. Part of the device for time distribution, part of it for time measurement. One of the use cases, and this is one that I mentioned before, using bidirectional SFPs and a link around 350 kilometers, I think it was basically providing time synchronization for the core or the central node part of a telecom network. So basically, all these blue and pink part of the network, we could synchronize that using White Rabbit. And we had a demonstration with Deutsche Telekom where we showed that the sub-nanosecond accuracy could be achieved using bidirectional distribution of time in those cases. Here we also validated all these WDM, White Rabbit over WDM distribution. However, again, I'm repeating myself a lot, but in some cases, I think it's important to make clear some points. When we go to long distance links with DWDM equipment, the pre-calibration is not anymore valid. So when we are in a data center environment, pre-calibration is great. You have plug and play links that provide you the precision and the accuracy expected from White Rabbit. But when we go to those long distance links, the asymmetries start to affect the time synchronization. So even when the White Rabbit maintains the precision, the accuracy, the offset from the actual correct time can can differ, and that's something that we need to calibrate. We have done that in different scenarios, and here this is a premiere. The first time that I'm presenting those results is something that we will publish in a couple of weeks in a journal. So these are production White Rabbit links deployed using telecommunication optical networks. We have a link connecting New Jersey and Chicago, so it's more or less 1,300 kilometers away one from the other, and we explore different ways to deploy the link. So in the first part of the experiment that we were doing here was to close just one hop of the link. The total link has 6 hops to connect New Jersey and Chicago. In this case, we were closing a loopback to the first hop, which was connecting Chicago and some point in Ohio. So this link was an 800 kilometer link approximately. And what we were able to do here, using a network effect calibration, we were able to achieve a mean offset of around 100 picoseconds. And you can see that the peak to peak from that point is more or less plus minus 450 picoseconds. So we maintained the sub-nanosecond stability in an 800 kilometer link using a telecommunication network using synchronous Ethernet compliant transponder. So basically a regular telecom network that you can find out there. This is actually the results. Well, this is the longest distance White Rabbit link that has been measured using a loopback, and we were not happy with that, so we went for the longest one in the world, basically connecting New Jersey and Chicago. In this case, we had 6 White Rabbit hops for long distance, but because of the fiber availability that we had, we were unable to close a loopback. So in this case, what we did was using a GNSS receiver in New Jersey as the time reference for our link, and we used a second GNSS receiver in Chicago to compare what we were receiving from New York in Chicago. So we were basically, it's like if you have in your table 2 different GNSS receivers, and you are connecting their pulse per second output to measure the time offset between both of them. However, instead of being in your table, one is almost 1,400 kilometers away. So in this case, using the GNSS-based calibration, we were able to achieve a mean offset of below 3 nanoseconds, and we were able to measure that the peak-to-peak was around plus minus 40 nanoseconds. Actually, regarding the standard deviation, which is close to 10 nanoseconds, what we found is that we had the GNSS receivers that we were using had a 15 nanoseconds RMS jitter. So basically, to obtain this result, this means that the GPS receivers were behaving more or less in a range of 8 nanoseconds RMS jitter, which is almost a 50% improvement to their specification before the White Rabbit link started affecting or contributing to the jitter itself. So although we cannot calculate the White Rabbit contribution to the jitter itself, what we see here is that the White Rabbit should be very precise in order to avoid the contribution of the GPS receivers. This is important in terms of right now that there is a lot of discussion about PNT sources especially in the US, but also in Europe. The estimated longest distance for a ground link for timing is something around 1,600 kilometers. So this is almost that distance, and the technology is still showing this sub-nanosecond or close to the nanosecond accuracy. So in case of data centers or where they are distributed in nationwide connections, this is basically showing that different data centers in different geographical areas could be interconnected with a very precise time synchronization. And this allows another part, which is the monitoring of multiple time sources. So if you are able to distribute one time source with very high accuracy to a different location where you have something to compare with, this can allow applications like for example, GPS accuracy measurement in different locations. It can be used also for if you have multiple PTP feeds coming to one location or different similar applications. So it's a tool that can help you even if you are not relying on White Rabbit for the production time synchronization. White Rabbit can be used to monitoring all the different time mechanisms that you have deployed in the network. For example, getting 5, I'm not sure, imagine Silicon Valley, you have 5 data centers, you can get the time reference from all those 5 data centers to a single one to compare how they are behaving one in comparison to the other. Then, and this, I don't want to extend myself that much in this part. There are many applications regarding defense, radars, radio over Ethernet, data acquisition, for example, in radio telescopes and things like that. But I don't think that they are that important. Again, GNSS backups. And one thing that is worth mentioning is the backup demonstration that we did for the Department of Transportation, where we showed that the White Rabbit technology was the most accurate in terms of time distribution, and also the only one that could provide full resiliency. And this can be used also, I'm not sure if in the context of data centers, but in industrial 5G and Internet of Things, terrestrial GPS systems using time synchronization to position different nodes in a certain area. White Rabbit can be used to synchronize all the different ground stations. Also in smart grids, where frequency distribution is used for different applications, and it can be combined with time synchronization. At the same time, White Rabbit has one important factor, which is deterministic data transfer, and this can be used in combination, for example, to time-sensitive networking (TSN) in different applications to send control instructions to the different parts of the network. And science, this is something that I think Majid covered much better than me, but just making a mention to this because it was where White Rabbit started. So I think this is the last slide that I have. There are some available use cases, some of them for finance, some others combining White Rabbit with different vendors or different applications that we have in our webpage.
Okay, so thank you very much. Let's see if anyone has questions. So the floor is open. Anyone has any questions?
About the technology White Rabbit uses for PTP, for example. I'm focused on mobile backhaul technology. We are currently implementing 5G, TDD 5G, and DSS 5G. So we are deploying an ATUT standard for that with SyncKey also. You know, you need to combine them. Regarding the last question I performed to Francisco, with moving for a mixing between with White Rabbit and this technology with the current technology I have. That's a doubt I have here in my mind. If you have picoseconds technology, I mean, which application need that picosecond technology?
Yeah, so that's one of the main questions. There are different use cases, and that was kind of what I wanted to show during the talk. One of the, I mean, if you are going for the picosecond side of it, where we typically see that is in distributed data acquisition. This is, for example, radio telescopes or particle accelerators. We see that also in radars. For example, radars, there are a lot of them that rely on frequency distribution. So this is the part where we are working on the picosecond side. But in the nanosecond side of the time synchronization, there are some applications in 5G where 5 nanoseconds, 10 nanoseconds are not mandatory, but are interesting for different applications. For example, positioning in industry, in specific parts of the 5G connected to Internet of Things. In those cases, the need of time synchronization is quite high. We also use White Rabbit to save time budget when we are distributing timing in telecom networks. Telecom networks are like have a lot of different hubs. They are geographically distributed. So if you can save part of the timing budget in one part of the network that is under control, for example, the core network that I showed in the Deutsche Telekom example, then this is some available time budget that you have for the subsequent layers of the telecom network. It could help also to distribute time references to discipline backup sources, and this is one question that I saw here. If White Rabbit can be used to discipline a Rubidium reference, yes, it can be used. White Rabbit can provide the typical frequency and PPS reference to those Rubidium clocks, so you will have backup sources in case that your main GPS fails in part of your network. And also, one of the main applications right now is finance. In finance, they are reacting to market events in the order of 20 nanoseconds. And in order to measure the latencies, they need at least to be 10 times better than the latency that they have. So with this sub-nanosecond accuracy in the different parts of the network, they are actually able to have visibility of the performance of their network. And this way, White Rabbit has been used in local deployment, but also interconnecting multiple locations.
Awesome. So we are on the top of the hour. Yeah.
Yep.
We're on top of the hour, and I'd like to thank Francisco for this great presentation today. And the recording, the slides will be all available on the wiki. Okay. I think that if more questions, please, you can use the mailing list, and then we'll go through it from there. Right. With no further ado, and we'll see you guys in 2 weeks.
Thank you very much for the presentation.
Yep. Thank you so much. Feel free to contact me if you have any further questions.
Great. See you, everyone.
Sure.